Okay, so now that we've kind of taken a look at how heat can affect the physical state and how we can relate that to temperature changes and our heating curve, let's take a look at another property of substances and how they affect the amount of heat that is transferred, either gained or lost, and then also how that affects temperature. And that characteristic of substances is the specific heat, or sometimes called the specific heat capacity of a substance. And we define that as the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius, right? So it's a measure of the amount of heat needed to increase the temperature of a certain amount of a substance by a certain temperature, 1 gram by 1 degree Celsius. Sometimes typical units that we'll see here would be joules per gram degree Celsius, or sometimes you'll see calories, unit of heat per gram degree Celsius, or essentially you could use any unit of heat, any unit of amount, any unit of temperature, but those are the most common ones that we will see. And we have here a list of specific heats of different substances. And as we take a look at these, you might see a general trend. And what I want you to focus on here is the substances that are all metals. So if you take a look, let's focus in on the metals on this table. So we have aluminum, for example. We have copper. What else? We have iron down here. We have mercury. Let's just use these three, and we'll look at their specific heats. And the thing to note about the specific heats of the metals generally is that they tend to have small or low specific heat values. So what does that mean? And how does that related to something that you may already know, but we may not have used the term specific heat to describe it? Well, you know from experience that metals tend to get hot very, very quickly. And by the same token, they tend to cool down very, very quickly as well. And the reason for that has to do specifically, no pun intended, with their specific heat, right? So aluminum, 0.215, it only takes 0.215 calories to increase the temperature of 1 gram of aluminum by 1 degree Celsius. And if you take a look at copper even, you only need 0.092 calories to increase the temperature of 1 gram of copper by 1 degree Celsius. And then iron is kind of in the middle, 0.108 calories to increase the temperature of 1 gram by 1 degree Celsius. So what this means, we can say generally that substances with low specific heats tend to heat up very quickly because you don't need to provide a lot of energy, a lot of heat energy to increase their temperature. And by the same token, they also tend to cool down very quickly as well. Okay, and especially when you think about in comparison to something like liquid water down here. Again, I'm going to pick water and we'll use copper as its comparison. So if you were to compare the specific heat for water with that of copper, it is about 10 times, water is about 10, has a specific heat of about 10 times more than that of copper. And what that means is it takes way more heat energy to increase the temperature of the same amount of water by the same temperature as it would for copper. Right. And if you can think about an application for that, well, where do you see copper things? Well, pots and pans at home, right? They tend to be metallic things because they tend to heat up very, very quickly. So they absorb the heat from the flame, and then they also give that heat into, or they transfer that heat from the flame into the contents of the pot or the pan, so that's able to heat up very, very quickly. So there's a practical use for this as well, but also as you are exposed to fire and other things, just keep in mind that metals, and you know this from experience, metals will heat up very, very, very quickly. And that has to do with their very low specific heats. Okay, so we can just compare these values and we can say if two substances are exposed to the same amount of heat energy, the one with the lower specific heat will attain a higher temperature than the one with a lower specific heat. And then the opposite of that would be true as well. Okay, so now let's see how we can make some practical use of the specific heats values. And what we're going to introduce now is something called the heat equation. I know we're all fond of equations at this point. The heat equation is very simple. What it does is it relates heat to the mass of a substance, to the specific heat of a substance, and to the change in temperature. And specifically now, the amount of heat we can calculate as being equal to the product of all of those three things. So the mass times, so the dot here means times, the specific heat, which we abbreviate as C. So whenever you see that lowercase c in a heat setting, that means specific heat capacity. And then the temperature change, or the change in temperature, we've used this notation before. We have our triangle, that means delta, change in, and then temperature, right? So the heat is equal to the product of the mass times the specific heat times the change in temperature. So if we know how much of a substance we have, if we know what the temperature was initially and what the temperature was at the end, and if we know the specific heat, which we can typically look up from tables, for example, like we've seen previously, we can calculate the amount of heat either being given off or the heat absorbed in order to account for that temperature change. Let's take a look at a simple example. So let's say a sample of, we'll use copper since we introduced that one before. A sample of copper has a mass of, let's say 25.6 grams. And let's an initial temperature of 15 degrees Celsius. And then we're asked what amount of heat is needed or is required to raise the temperature of this sample, let's say now to 79 degrees Celsius. Okay, so again, when you see, a question like this, and most questions, you're not told, right? You have to use this equation. This is what you have to figure that out from the problem, and just approaching the problem itself tends to be a challenge in most cases. So I find the best way to do this is just to organize the information that you have, right? So we're told we have first of all, we have copper. So we have that, we know the identity of the sample. It has a mass of 25.6 grams. We have an initial temperature. So initial temp here is 15 degrees Celsius. And then what we need to find is the amount of heat needed to change that temperature from 15 to a final temperature of 79 degrees Celsius. So what we can determine from this is that change in temperature. And the change in temperature, the change in anything, is always the final minus the initial. So right away, we can determine the change in temperature as 79 minus 15, and that would give whatever, 64 degrees Celsius. That is going to be my delta T. Okay, I have my mass as 25.6 grams. If I need to find heat, then I'm probably going to use the heat equation. So EQN is my abbreviation for equation. Let's write that down here. So we have the heat is equal to the mass times the specific heat times delta T. Okay, so I'm going to substitute my values. The heat is the mass, 25.6 grams. C, my specific heat, I can look this up in the table. You don't have to memorize the specific heat values. You'll either be provided with them or you can look them up. So for, what do we have? Copper there, it was 0.092 calories per gram degree Celsius. So that's 0.092 calories per gram degree C. And then my change in temperature, delta T, was 64 degrees Celsius, right? So I'm going to multiply all these together. And what you'll see, hopefully, is that the units are going to cancel. So grams cancel here, degrees Celsius cancels there. And I end up with calories as my unit, which makes sense because I'm trying to find heat. So if I plug this into my calculator, I'll be able to find the heat that's needed. Okay, so my handy dandy calculator here, I get 150.7328. So if I just follow my rules for sig figs, I have 3 sig figs, 2 sig figs, 2 sig figs. So my answer then should have 2 sig figs. I'm going to round this to 2 sig figs. That's 150 calories would be the amount of heat that's needed to raise the temperature of 25.6 grams of copper by 64 degrees Celsius. Now, we can do a quick calculation to compare. Let's see if we were to do the same thing. Okay, well, we'll do this really quick just to do a comparison here. Let's say you have, so if you have the same amount and the same change in temperature, how much heat will be needed for a sample of water instead? Okay, so we have the same amount of water, 25.6. We have the same temperature change from 15 to 79, so that's 64. Let's calculate how much heat is needed to change the same amount of water. So we're going to use the heat equation again. So the heat will be the mass of water, which is the same mass. We're just assuming it's the same, times the specific heat. Now the specific heat for water is different, right? So it's 1.00 calories per gram degree Celsius. So that's 1.00 calorie per gram degree C. And then the delta T is going to be the same, 64. So we substitute those values, 25.6 grams times 1.00 calories per gram degree Celsius. And then my change in temperature is 64 degrees C. Degrees Celsius go away, grams go away. So if I stick that in my calculator again, okay, now I have 25.6 times 1 times 64. Okay, and I end up with 1,638.4. So we round that to 2 sig figs. That's 1,600 calories. Okay, so now I can do a really, really quick comparison here with these two values, right? If we have the same amount of two different substances, we have copper here at the top, 25.6 grams of copper. We have 25.6 grams of liquid water on the bottom. we want to increase their temperatures by the same amount, by 64 degrees Celsius, it takes more, actually more than 10 times as much heat for the water to increase its temperature compared to the same amount of copper that we have, right? And again, that has a lot to do with just the much lower specific heat of the copper, the metal, compared to water itself. So the specific heat equation, we can use that equation to find heat. We can also use it to solve for any of the variables in that equation. We can rearrange this equation. So let's just show you that really quick. Okay, we can rearrange this to solve for any variable in that equation. So for example, I can determine the specific heat, right? If I don't know what a sample is, but I do know how much heat I provided to it, I know what the mass of it, I know what the temperature change, I can actually determine the specific heat experimentally and then compare it to a known set of values to actually identify what that substance is. So in this case, the specific heat there would be equal to the heat divided by the mass times the change in temperature. I just rearrange this equation and I end up with I can do that with any of the other variables in that equation. We just do a little bit of mathematical massaging to the equation to solve for any of the unknowns. And when we get to lab, the next time we'll actually do an experiment that looks at specific heat, and you'll be determining the specific heat for at least one or two different metals.